Once Optuna finished its experiment, you save the result using study.best_trier. So in here, you can find the best.prompts to have a best prompts. So once optimization is finished, what you need to do is using Optuna, you find the best set of prompts. And then what you need to do is redefine the function and use the best hyperparameters and train the model and save it to use it for the other cases or model deployment. So I define it and then retrain the model from the initial parameter. So by doing so, I can check the result of my model. So in the cross validation, R square, the best R square was 0.51 with this hyperparameter. When I train the model with that, I get this result. There is a criteria to check if the model performs well. You check cross validation R square. Let's say cross validation, which should be higher than 0.5, and you check external test set R square, which should be higher than 0.6. That's the criteria. But when you develop the model, you can use other metrics. So here I use only R square, but what if my model is not um, satisfying this condition? It's still okay because you can measure your model's accuracy with the RMSE, root mean squared error, and NRMSE, normalized root mean squared error. And it's calculated with this RMS is divided by the range of endpoint, which means minimum value and maximum value of um, endpoint, in this case PLC50 value. PLC50. Oh, actually max should be here. Max and mean. Ooh. Okay. Max and mean, minimum value. It is used because RMS is increasing if the range of the endpoint is larger. For example, there is a melting point prediction model, and the data set has a range of melting point like this, minus 100 degree to 5000 degree. In that case, model RMS is easily going beyond 100. So that doesn't mean the model is inaccurate. It's just quite large because endpoint range was quite high. So we try to normalize RMSE value. So if RMSE divided by the range of endpoints is lower than 10%, we consider that this model is highly accurate. So even though R square doesn't meet this criteria, but normalized RMSE is lower than 10, then so I should multiply 100. In that case, model can be still useful. Another metric is called Spearman's correlation. So there's a compound from 1 to n, and if we know PLC50 value, we can rank the compounds from the highest PLC50 value to the lowest PLC50 value, and let's say this is the rank of toxicity. And we can rank the compound with the prediction value. Okay, and then we compare the rank of observation and prediction. We can compare this rank of these rank by the observation value and rank by prediction value can be compared, and Spearman's correlation estimates how the rank were dissimilar. So this, if the Spearman's correlation is higher than zero point 0.6, I can say the model is still useful, because model is sometimes used to prioritize the compounds. Its aim is to find the compounds with higher toxicity than other compounds. So if the model can find a good ranking, so if the compounds ranked pretty correctly with the prediction value, like the rank decided by the observation value, then we can say that models can be useful to find the toxic compounds compared to the other compounds. So it's a quite relative way of comparing the prediction values, and it's also a useful way of using the model. So we also check Spearman's correlation sometimes, but in this course I didn't use that. But if you're working to develop the model, I suggest to test your model with these three metrics. So this is the result, and the last part of this is check um, author's prediction value. So we are taking data from the research article. So here you see the author also developed a model, which is a linear model. So this experimental value is observation, and this is a prediction value from the research article. So by comparing these, actually we can measure the model accuracy, prediction accuracy of the model in the research article. So I'm trying to get this value. So I need this value to calculate the prediction accuracy of the model in the research article. So that's what I did. This is a prediction value and this is the experimental value. I'm saying this is observation and this is a prediction. And use it to calculate the prediction accuracy of the model. So it's 0.87 and my model is 0.83. So model in the research article is better than mine. And this model comparison is one of essential part if you are developing the model, because reviewers will be curious about how good model your is. So normally they suggest to compare your model with the other data or other model. So here I do that, and thankfully the supplementary information provided prediction values, so I can check prediction accuracy of the model in the research article. So if it's not successful, well, I tried to improve the model than the model in the research article, but I failed. So in that case, I can try again with more hyperparameters or other algorithms as well. So machine learning project is actually endless. It's like an endless loop. So you develop the model and you did it again and again until you get the satisfactory result. And it's not, then I'll run again. So this is where machine learning project requires a large computational resource, because we need to run a lot of experiments, and having a better computational resource can reduce this time significantly. So as you see, one uh, running just one time of developing the model is not really um, tremendous. But if you're in the project and you want to find the best model, then you really need to test a lot. So that's it for the hyperparameter